Hello, everyone, and welcome. So, have you ever actually wondered why we use a giant roaring furnace for iron, but a super high-tech electrical process for something like the aluminum in your drink can? Well, you're in exactly the right place. Metal extraction can seem really tricky, but honestly, it's a puzzle with one very simple key. In this explainer, we're going to give you that key and show you exactly how to unlock this crucial SPM topic.
But before we jump in, just remember, understanding this stuff is only the first step. To really master it for your exam, you've got to practice. So after you're done here, I seriously recommend you head over to mcqspm.com or just scan this QR code. It's the absolute best place to apply what you're about to learn with real past year questions.
All right, so here's our game plan for today. First, we're going to start with the single most important concept, the reactivity series. Then we'll get into two huge case studies, aluminum and iron. After that, we'll put our knowledge to the test and tackle some real SPM questions. And to wrap it all up, we'll look at the bigger picture, the true environmental cost of it all.
Okay, let's get right to it. Seriously, everything, and I mean everything we talk about with metal extraction boils down to this one simple list, the reactivity series. If you get this, you've pretty much unlocked the entire topic.
That's the big question, isn't it? Why the massive difference? You've got this huge, fiery furnace for one metal, and then this powerful electric current for another. It sounds complicated, but the answer is actually really simple. It all comes down to a chemical tug-of-war with one key element. And here it is, the master key. The whole story is right here, and the main character you need to focus on is carbon. Okay, think of reactivity as chemical stubbornness. The metals up top, above carbon, like aluminum, they're incredibly stubborn. They hold on to oxygen so tightly that carbon just isn't strong enough to pull them apart. For these guys, we need a chemical sledgehammer, electrolysis. But the metals below carbon, like iron, they're less stubborn. Carbon is strong enough to just step in and snatch that oxygen away. We call that reduction. And way down at the bottom, you've got gold and silver. They're so unreactive, they don't even bother bonding with oxygen. You just find them as pure elements. So the golden rule is super simple. Just ask, is this metal more stubborn than carbon? Right, let's move on to our first case study and see this in action. We'll start at the top of the series with aluminum, a very reactive metal that, you guessed it, needs a very powerful solution. So just like we saw on the chart, aluminum is way more reactive than carbon. You could heat aluminum oxide with carbon all day long, and literally nothing would happen. Carbon is just completely outmatched. It's like trying to win a tug-of-war against someone twice your size. It's just not going to work. To break that super strong bond between aluminum and oxygen, we've got to bring in the heavy machinery, electricity. Now here's a little detail that examiners absolutely love to ask about. Aluminum oxide has a crazy high melting point. We're talking over 2,000 degrees Celsius. Trying to melt that would use an insane amount of energy and money. So chemists found a little hack. They add this stuff called cryolite. Cryolite's one and only job is to lower that melting point to a much more manageable 1,000 degrees or so. Now here's a super common mistake students make. They call cryolite a catalyst. It's not. It doesn't speed up the reaction, it just lowers the temperature needed to get it started. Please remember that. So what's actually happening inside the electrolysis cell? Well, it's pretty simple. Opposites attract. The positive aluminum ions, the Al3+, they get drawn to the negative electrode, which we call the cathode. There, they gain electrons and get reduced back into pure molten aluminum. At the same time, the negative oxide ions, O2-, are pulled over to the positive electrode, the anode. They lose their extra electrons and are oxidized to form oxygen gas. Just remember oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Easy peasy. Okay, so let's contrast that high-energy process with something a bit more old school. We're moving down the reactivity series to iron, a metal that is less reactive than carbon. And this means we can use a much more clever chemical approach instead of brute force. And this is the tool for the job, the blast furnace. This thing is basically a giant continuous chemical reaction tower. We feed it three key things from the top: iron ore, which is mostly a compound called hematite, coke, which is almost pure carbon, and limestone. Let's break down what's happening zone by zone. Way down at the bottom, in Zone 1, the coke burns in super hot air. This creates crazy heat. That heat makes the carbon dioxide gas rise up to Zone 2, where it reacts with even more hot coke to form carbon monoxide, CO.
Now, this is the real hero of our story. In Zone 3, it's the carbon monoxide that does all the work. It's the main reducing agent, stealing the oxygen away from the iron ore to leave us with pure, molten iron.
But wait, what about the limestone? Well, iron ore isn't perfectly pure. It's mixed with a bunch of sand and earthy junk, mostly silicon dioxide. So we add the limestone to get rid of that rubbish. The heat breaks down the limestone into calcium oxide, and that reacts with all the sandy impurities to form this molten waste product called slag. Just think of it like soap scum that traps all the dirt. And the best part? The slag is less dense than the molten iron, so it just floats right on top, which makes it super easy to skim off.
Okay, so we've got the theory down. Now for the most important part. Can you actually apply it when you're under exam pressure? Let's take a look at how these exact concepts pop up in actual SPM questions.
All right, here's a classic from the 2010 paper. Go ahead and pause right here and see if you can solve it yourself. The question is asking which of these metals can you get using carbon? That's the key, reduction using carbon. Okay, let's walk through this just like you would in an exam. The second I see reduction using carbon, my brain immediately goes to our master key. This only works for metals that are less reactive than carbon. So let's check our list. Iron, yep, less reactive. Tin, also less reactive. Aluminum? No way, that's more reactive, needs electrolysis. So we can immediately eliminate options A and D. Magnesium, even more reactive, definitely needs electrolysis. So C is out. The only ones left are iron and tin, which means the answer has to be B. See how fast that is when you use the master key?
Let's try one more. This one's from 2012. You know the drill, pause and give it your best shot. This one is testing that very specific but very common detail about aluminum extraction. What's the point of cryolite?
This should be an instant reflex by now. The moment you see cryolite, a little alarm should go off in your head that says, melting point hack. Its only job is to save a ton of energy by lowering that crazy high melting point. So let's check the options. A, act as a catalyst? Nope, that's the classic trap we talked about. B and D are just not relevant. The answer is clearly C. It lowers the melting point. That's an easy mark, if you remember the hack.
You know, chemistry isn't just about what happens in a lab or a giant factory. It has massive real-world consequences. So let's talk about the true cost of getting that shiny aluminum for our cans. Getting aluminium from its ore is actually pretty tough on the planet. First, the electrolysis process uses a staggering amount of electricity, which often comes from burning fossil fuels. That, plus the reactions at the anode, releases a lot of CO2, a major greenhouse gas. And on top of all that, when you purify the bauxite ore to start with, you create this nasty toxic byproduct called red sludge, which is a huge environmental headache. But there is some good news here, and it's a really, really important piece of good news. Check out this number, 95%. Recycling an old aluminum can saves 95% of the energy you need to make a new one from scratch. Let that sink in. 95%. That means all those problems we just talked about, the insane electricity use, the CO2 emissions, the toxic red sludge, they're almost completely avoided just by putting a can in the right recycling bin. So the next time you hold a simple drink can, I hope you see it a little differently. It's not just a piece of metal, you know? It's the end of this incredible chemical story that all starts with that simple list, the reactivity series. And knowing its true environmental cost, well, it makes that simple act of recycling feel a whole lot more important, doesn't it?